This is a quick video about crystals. So as you can see, they all have different shapes. The main idea here is the metals are much stronger, but they're brittle. And your semiconductors are much more ductile, but they're inherently weaker compared to. When you fuse them together, you have a variety of different materials and products you could use around the world. Semiconductors, you make computers, you can make lasers, armor, any sort of thing with structures and whatnot. The main idea here is that they're very different. So your metals, like titanium right here and molybdenum, they're considered a body-centered cubic, and they have a coordination number of 8. What that means is they have an atomic packing factor of 68%, meaning they're essentially a little more compact compared to your semiconductors. You can see it a little better there. Whereas your other one, for your cadmium and cesium, is only 74%, so it's even more compact. Coordination number 12. Yeah, so that's the main difference between the two. And there's all your map there, you can explain that. There's not really there's not an easy way to explain it. The primary reasoning for doing this math, for that particular reason, aside from getting the credit obviously, is trying to see how it behaves in a certain environment. Obviously, when you heat the thing, it's going to behave differently when you heat it up compared to if it's cold. Like metals can be much more brittle. When it's cold, it's going to break easier. And when it's hot, it's going to be more malleable. You can bend it and all that. Or forge it, you got a hammer big enough. Yeah. Then obviously there's further math for the second part. But the main thing, the really important part of this project is identifying the shapes and the crystal structures. Like you see how these are all packed together. The little black ones here are like, I guess you'd call deformity or impurities in the actual unit cell. Whereas this one is more of a hexagonal shape, but it's still considered packed. This is basically a side-by-side. These are essentially very similar, but each from a different angle or perspective. So this would be from the plane looking right at you. This would be from the side plane, like your x-axis. Yeah. And then down here, talk about linear density and planar density in the theoretical and the actual. So your theoretical density is kind of like a Riemann sum. It's always going to be an under or an over approximation. It's never going to be precise. And if you're really precise, you're probably good at math. But most of the time, it's not quite what you think it's going to be. And all these values here calculate up here. These are just formulas for you. So your linear density, we're talking about length. That's kind of assumed when you say linear, it's going to have to do something with a plane. So obviously it comes down to the direction vector divided by the length, and then your planar, same exact thing, just now we're talking about atoms centered on the same plane. That's why they're related to each other. But the main difference, your linear has to do with length, planar has to do with area of atoms. And when it comes to the lattice structures, you have to consider the constant A, the lattice constant, when you're actually multiplying and calculating what they are. I found all these on the computer, and basically there are two or three different groups basically. Like your metals are always going to be BCC. Yeah, basically it's going to be kind of like that. It's going to be all centered, really tight knit, close. So your corners and your centers of the unit cell will be based on that, like 120, 210, 101, yeah, something like that. Like that's molybdenum. That's the strong metal. Titanium is actually considered HCP. HCP has the same structure as cadmium, which as you can see they're very different. But they have the same unit cell atomic composition, if that makes sense. The only difference is in titanium it's on the vertices, so like on the sides. Whereas for cadmium, it's going to be on the parallel plane to the hexagonal faces. So like it'll be there instead of being on the side where the imaginary triangles are. It's kind of weird, but that's how it works. And then for